Good afternoon, everyone. I'm Diego Russo, and today we're going to explore something exciting in CPython, the just-in-time compiler. A bit of disclaimer, this presentation has been given a EuroPython this year, so if you saw, and it's going to be exactly the same. The only thing I've changed is just the subtitles there. It's going to be exactly the same. And then I thought, yes, okay, it's still relevant. So I thought I volunteer to cover the gap for the PyCon UK. So before we start, a quick raise hand exercise. Raise your hand if you know what a JIT is. Right, that's great. Raise your hand if you knew that CPython has an integrated JIT in the runtime. Less. Now the pro users. Raise your hand if you ever used the CPython JIT. Whoa, only one person. No, this is great because independently of your level of understanding or the experience you have, this talk is going to give an overview of what the CPython JIT is. And this is the official Python runtime, finally growing a just-in-time compiler. And it's happening as in the interpreter we use every day. So I'll walk through how it works, what it looks like in action, and how you can use it. We're going to look at the Python internals, including bytecode, JIT mechanics, even a bit of assembly and machine code. So if you're not used to that, don't worry, I'll keep things visual and hopefully focusing on the big picture, so hopefully you can follow along. So I've been writing Python for almost 2 decades, and I've spent the last 14 years at ARM working as a principal software engineer in the runtimes team now. I'm also one of the leads of the Python Guild at ARM, which is a company-wide community with almost 1,500 people. And I've been contributing to Python and its ecosystem for the last couple of years, focusing mainly on performance and internals. In particular, I spent the last year and a half working on the experimental JIT compiler, and a few months ago in May, I became a Python core developer. So what is a JIT compiler in the context of Python? So a just-in-time compiler is a component of the runtime that identifies frequently executed portion of code that what we call hot code paths and compile them into native machine instructions while the program is running. So this gives us the best of the both worlds. One side, the flexibility of the interpreter execution for most of your code, and the other side, the performance of the compiled code for the parts that matter the most. So in CPython case, the JIT is a tracing JIT. So it observes how the code behaves during the execution. It builds traces, which are linear paths through the control flow, and at the end, it compiles those traces into fast native code. Then these traces are not general purpose functions. They are specialized paths that avoid type checks and the interpretation. So once the JIT takes over, we completely remove the interpreter overhead for that specific path. So let's talk about the strategy that CPython uses to implement the JIT. It's called copy and patch. This is quite different from the heavyweight just-in-time compilers that builds and optimize entire functions on the fly, for instance, using LLVM or custom intermediate representation. Instead, CPython approach is very simple and pragmatic. For every micro-operation, for example, things like loading a variable, doing an integer multiplications, or jumping to the next iteration, the JIT has pre-compiled machine code stencils already built in an interpreter. When a trace becomes hot, the JIT copies these code stencils into memory, and then it patches them with the runtime-specific values, like things like constants, memory offset, jump targets, and etc. These patch fragments are then linked together and executed instead of interpreting the original bytecode. There are some important benefits to these designs. It avoids the need for a full dynamic code generator, which reduces the complexity. It's portable. This means that it works cleanly across platforms, including ARM and x86, and is maintainable. It just reuses known good code paths and they're specialized per trace, rather than trying to compile some random Python logic. So it's worth asking, why is CPython adding a JIT now, and what had to happen first? So in 3.11, we had the specialized interpreter. This is an interpreter that runs regular bytecode, and as the program executes, it rewrites the hot bytecodes on the fly with more specialized versions. So this mechanism gathers runtime data, things like types, branch outcomes, and defines which bytecodes are hot. And all this information are critical for a later compilation. 3.12, we have a DSL, a domain-specific language for generating the interpreter code. So this helped managing the complexity and remove a lot of boilerplate code like stack manipulation and reference counting. We now have a single source of truth to generate multiple tiers of interpreters. 3.13, there is a new micro-op interpreter that was added. It lowers the specialized bytecode into micro-ops, which are simpler and easy to optimize. This new pipeline detects hot code and runs more efficiently. This is also the first implementation of the JIT is in the code base. And now in 3.14, the experimental JIT is more accessible to user. It improves micro performance, and it adds the infrastructure for better code stencil generation. So the JIT is not just something that happened overnight, but is a result of many years of foundational work to modernize the CPython execution pipeline. So let's go more in details on how the JIT works in 3.14. So we're going to see a high-level execution pipeline in 3.14 from the Python source code all the way down to the native machine code. So it starts, as always, with your Python source code. The CPython internal compiler parses into an abstract syntax tree. It builds a control flow graph and applies some basic optimization and eventually emits bytecode. That bytecode is then executed in the interpreter. So while running, it collects profile information, what types are used, which bytecodes are hot, and how the value flow through the code. Based on that, the interpreter starts rewriting bytecode instructions with more efficient and specialized versions, the ones that assume specific types or behavior. Then when a loop becomes hot enough, CPython lowers that specialized bytecode into micro operations. These are low-level fixed-purpose instructions designed for easier optimizations. The next step is to take these traces of micro-ops and apply further simplification to produce an optimized micro-op trace. And finally, that optimized trace is passed to the JIT, which uses the copy and patch technique. It assembles native machine code functions by copying the code snippets for each micro-op and patching with the runtime details. That native trace now completely bypasses the interpreter for that specific part of the program. It's faster, it is running hardware instructions. Now that we have seen the big picture, let's follow the concrete example through the entire pipeline, execution pipeline. So here's a function we're going to follow in detail. So it's called sum squares. It's a very simple loop. It initializes a total, iterates over a range of n, and it adds I times I to the total and returns the total. So despite being simple, there are all the right ingredients to demonstrate the CPython JIT. So we have a loop which can become hot, integers operations, and a structure that can be easily loaded into micro-ops and optimized. So let's focus on the for loop. And this is the respective bytecode for the specific for loop. It's not for the entire function, but just for the for loop, before any specialization or tracing happens. The compiler emits general-purpose opcodes like for iter, which control the loop over range, and load fast for loading variables like I and total, and two generic binary op instructions, one for I times I and the other one for plus equal. These instructions, so the binary op and the others, are intentionally broad. For example, the binary op handles any Python multiplication or addition, whether it's an integer, floats, list, or even user-defined objects. So this flexibility is great, is what makes Python great, but it's not that ideal for performance. And in a moment, you'll see how the CPython rewrites some of these instructions at runtime based on the observed types to make them faster. As this function runs, CPython interpreter starts rewriting the bytecode based on what it observes at runtime. For instance, if n is an integer and it sees that I and total are always integers, it can replace the general binary op instruction with a faster type-specific variance. In this case, the binary op for the multiplication becomes binary op multiply int, binary op plus equal becomes binary op add int, for iter might become for iter range, because we assume it's iterating over a range object. So these specialized instructions are faster because they skip dynamic type checks. So they assume the type, and they are correct as long as the runtime guards hold. So there are two things to highlight here. These changes are done automatically and incrementally, so the interpreter evolves as your program runs, and there is no need to recompile or restart. It's all dynamic and happening at runtime in background, and this is happening since 3.11. So once the bytecode is specialized in and the function runs enough times, CPython takes the next step. It lowers the bytecode into micro-ops. So each bytecode instruction is broken down into multiple micro-ops, which are simpler operations with well-defined behavior, such loading a variable, performing an integer multiplication, or storing a result. We'll see how this bytecode will be lowered into micro-ops. And this is a small animation that basically every bytecode instruction is broken down into different micro-ops. And what you see here is a trace, which is a straight line execution path extracted from the running function. It contains only the operations that actually happen, and there are no branches and no abstractions. So once the bytecode is lowered into micro-ops, CPython doesn't immediately hand that off to the JIT. Instead, it performs a few simple but effective optimizations on the specific trace, and as you can see here, in the example, some of the generate load fast and store fast instructions have been replaced with a more specific optimized variants, like load fast 1, store fast 2, and so on. These aren't just name changes, but reflect the actual memory slot numbers in the local variable array. For example, load fast 1 means load value from the local variable slot 1, and store fast 2 means store a value into the slot 2. One more optimization that can happen with this phase is the removal of redundant checks or guards. For example, if the JIT inserts a type check to ensure a value is an integer before a binary op, then that sees that the same checks already occurred early in the trace, it can simply remove it. This kind of redundancy is common when a loop or a block performs similar performance repeatedly with the same types. And the result is a cleaner, tighter micro-op trace, which is faster to compile and to produce a better machine code. This step is important because it balances performance and simplicity. So we are not doing a full-blown compiler optimization passes here. It is just enough to make the generated code smaller and faster without adding too much overhead. So once we have an optimized micro-op trace, CPython takes the final step. So it generates native machine code. And this is done using the copy and patch approach that we introduced earlier. So for each micro-op, there is a pre-compiled machine code template, which is a short sequence of machine code instructions that implement that specific operation, that specific micro-op. The JIT copies these templates and patches them with the runtime details. These details are like instructions and address relaxations, memory locations, variable slots, and jump offsets. Now we see how these micro-op trays will be converted into machine code. again, a small animation that basically we see that every micro-op is replaced with a machine code. And once patched, these pieces are linked together into a single executable block. That block is then called directly, bypassing the interpreter. So what's clever here is that CPython avoids building a full code generator. It just reuses fast machine code fragments and stitches them together efficiently. This makes the system portable and much easier to maintain than a traditional JIT. Now, with the next set of slides, I want to explain how a template is generated by a micro-op implementation at build time and how the patch works at runtime. So by build time, I mean when we compile CPython. And at runtime, I mean when we run our Python application. So let's take a closer look at the underscore setIP micro-op. Its job is to update the instruction pointer for IP of the frame. So it's a very simple job. And this is literally the code that implements it. We load the value of the operand, which is a pointer to the next micro-op instructions, and then set the new frame instruction pointer. When the micro-op setIP is selected for the JIT compilation at build time, so again, when we compile CPython, its implementation is wrapped inside a standard C function template, like this one. This function is not for the entire trace. Again, it's designed to execute a single micro-op with all the necessary runtime context. And it takes 3 arguments: the current interpreter frame, the stack pointer, and the thread state. These are passed because any micro-op might need access to them. For example, in this case, underscore setIP needs only the interpreter frame. Also, I picked these setIP because the implementation is very simple, so you can follow along, but other micro-ops, the implementation is much more complicated. So inside this function, you'll see also several patch values placeholders. These are the fields that will be patched at runtime. And these are things like the actual micro-op to execute, its operand, and the target address or continuation point. In this case, setIP, the operation is very simple. It set this frame instruction pointer to the value of operand 0. That operand, which is the new instruction pointer, will be patched just before execution. So once patched, this becomes a fully functional micro-op execution unit ready to be called from within a trace. And this is what the JIT wrapper for setIP looks like after it's compiled, but before it is patched. So this is a short sequence of arg64 instructions that implement the core behavior of setIP, updating the frame's instruction pointer and jumping to the next micro-op. Let's walk through the instructions. So the first one is an address page. This loads basically the page address of the JIT operand 0 symbol, which will be patched later with an actual value. The second instruction is a load register, which loads the full 64-bit operand, which is the new instruction pointer into register X8. The third instruction is a store register. So it stores that value into the frame instruction pointer field. On arg64, X20 holds the frame pointer, and the offset is 038. It corresponds to the instruction pointer field. And the last instruction is a branch. It is a branch instruction that basically jumps to the next micro-op functions. So JIT continue should be patched with a correct continuation target. You can also see the relocation tags. These are marks where the runtime linker, or in this case, the patching logic, will fill the real operand and continuation values. So even though this code looks static, it's actually just a template or by other terminology is a stencil, that can be executed once it has been patched. And this is the C function that defines how the machine code for set IP is emitted at runtime. So it lives in the CPython JIT backend, and it sits next to other hundreds of emit functions, one for every micro-op implemented. The code body array that you see here is the binary representation of the instructions that we saw earlier, the assembly instructions. Yes, it's the same ARC64 sequence that performs set IP. This is what we call the stencil. It's a small precompiled machine code template that implements the logic for a single micro-op. When the JIT needs to emit set IP, it simply copies this array into executable memory and patches the right operand's value. So rather than generating new code every time, CPython uses these reusable stencils to keep the JIT simple, fast, and somehow portable. And this specific function does three things. So it patches the operand using patch64, which writes the actual runtime value. It copies the stencil into the code buffer with memcopy. And then it calls patch arc6433rx, and this is where things are a little bit clever. This specific function tries to relax the code. What does it mean? So it means that if the operand is close enough to the instruction pointer, the patcher can rewrite the address page plus load register, so the first two instructions that we saw earlier, into a more efficient instruction, like a load register with a PC relative offset. So once we have our stencil generated at build time, here let's see how it is emitted at runtime, so when we execute our application. So this is the actual machine code for set-IP shown before the patching. So these are generic instructions that still refer to symbolic addresses like JIT operand 0. So this cannot be executed because it's not patched. We don't know where to go. Notice something important here. This code is slightly different from the one that we saw in the previous slide. We have replaced the final jump. If you remember, the last instruction was a branch instruction with a no-op instructions. And this happens already when we generate these stencils at build time, so when we compile CPython. And this because we just need to fall through the next micro-op without using any branch instruction, which would be more expensive to run. So we just remove the branch and we go through the next one. Then the JIT that patches the stencil with runtime information by calling the three functions that we saw earlier in the emit function. And now we have the patched code in the executable memory. In this specific case, the JIT backend has rewritten the first two instructions to use a more direct addressing mode, replacing the address page load register pair with a single literal load register. And this is thanks to the optimization logic that we have in patch arc6433rx function, which detects when we can relax the stencil, meaning that we can generate a shorter and faster code because the operand fits in the simple form. And after all these optimizations, the result is a smaller and more efficient native sequence. So we have two actual instructions instead of the initial four that we had at the beginning when we saw the code. And at this point, once has been patched, this is ready to be executed. So where does these leave us? So the JIT that you've seen is real. It's in 3.14 and is evolving very quickly. But it is still marked as experimental, and this is what actually means. So performance are, of course, workload dependent. In some cases, the JIT can deliver up to 20% in 3.14, but for others, you might see no benefits or even a small slowdown. There are also some important limitation. It's not compatible with a free threading implementation yet, hopefully in 3.15 we'll fix that. You need LLVM to build a stencil when compiling CPython, so LLVM is a hard dependency when compiling CPython, independently if you compile CPython with GCC. And there is currently no native debugger integration, so tools like GDB, Perf, or System Profiler cannot unwind through the JIT frames yet. So the JIT today is supported on x64 and x86, and the three main operating systems, so Linux, macOS, or Windows. So very, very likely you can try it out. Also 32-bit Windows is supported as well. So what's next? So looking ahead actually is more looking at the present, because we are already working on the 3.15 implementation. So of course, from the JIT point of view, we want to make JIT faster and more robust. On the performance side, there are already things happening, so like reducing ref counts, top-of-stack caching, improving micro-optimizations, integers or float unboxing, and also generating better stencils that produce better native code. At the same time, we're also working to address the two limitations we said earlier about the free threading and the buggers. So if you're curious or excited or just want to try it out, this is the perfect time to try it. So you can already evaluate and test the JIT today, but not in production. It's still experimental. So if you want to play with it, feel free to do it. Also, on the builds, on macOS and Windows builds of the 3.14, the JIT is built by default. It's built, but it is disabled by default. So you need to enable it at runtime. And on Linux, you need to basically recompile Python. So once enabled, then you have modules where you can inspect things about the JIT with a _JIT module. And again, if you have issues, file a bug. If you see something unexpected, again, share it. And if you want to see how it is implemented, the code is in the standard CPython GitHub repo. So as a last thing, I want to show you a very simple but not so live demo. So this is just a screenshot I took of the JIT in action. Doing demo live is very dangerous. So we have the same function that we saw earlier that during the presentation. It takes 100,000 as an input, and we run it 500 times just to generate some workload. So we firstly run with the JIT disable, so with a Python, well, with a JIT disable without, well, I set the Python JIT equal 1 to make sure that it's disabled, and then the second run with the Python JIT equal 1. And as you can see, the non-JIT version takes 6.5 seconds, while the JIT version runs about 5.6 seconds. We get 16% speed up on this specific case, and just by setting an environment variable. So there are no code changes, no extensions. This is just by enable the JIT in CPython. Again, this is a very small example, but shows how even a small loop can benefit from it. So these are a few references I used to create the presentation. I'll leave it here for later consultation. And I guess that's it from me. I hope this gave you a useful overview of the JIT, what's happening in the CPython JIT, maybe convince you to try it out. I think we run out of time.